alpha particle scattering experiment provides evidence for the existence and small size of an atomic nucleus compared to the overall size of the atoms. Okay, so you remember the alpha scattering experiment. I'll briefly go through it. B5A1 part 1 and part 2. I'll put it here, part 1. So this experiment is a very simple experiment. You have gold paper, so you have the gold atoms on the paper here. And what happens is, the gold atoms, Rutherford fired alpha particles through the gold leaf paper. So most of the time the alpha particles pass through. However, sometimes they hit a nucleus and bounce back, or they swing around the nucleus or whatever like this. But because most of the time they pass through, this actually tells us that the atom must not take up much space. So the first answer would be most of the alpha passed through the gold leaf. Only some deflect or reflect. Therefore, the atom occupies a small area, volume, I suppose. Okay, we'll go with space. A small space. It just sounds stupid. That's why I wasn't sure. But the atom occupies a small space in the gold leaf in the paper. Golf leaf? That ain't right. Gold leaf. And then in part 2, how does this prove that the nucleus is positively charged? Well, with a picture it helps. Yeah?
Just lost it.
So, if it was a positive charge and the alpha particle is positive, then what would happen is here it would stick, or it would get repelled if they were both positive. Alpha is positive, so if they're both positive, it repelled. So it could either get deflected, or if it hits it perfectly straight, it would return. But if the center was negative and the alpha is positive, what would happen? Yeah, it will, when it gets close, it gets attracted. So it could get repelled, but if it hits it straight on, it might stick to it instead of coming back, you know. So it's the fact that they get reflected and repelled that show that the center must be positive. So because the alpha is reflected and repelled, this implies that the center is large and positive. My pen's gone. Back to mouse mode. Large and positive. Ugly.
What's the line?
The center of the nucleus. In other words, KJ, I'm saying that it must be a big positive particle at the center, because
Well, I don't see love being because in the other
I suppose
question said it's small.
this is the thing which we cannot see because of the level of physics we have. But Rutherford, by calculating the angles that he got from the experiment, was able to show that the nucleus must be at least the same, that the center must be at least the same size as the alpha particle.
Yeah, because if it's small,
If it was smaller, then the behavior would be different. In fact, the maths involved in it is way beyond this course. It's something you might do in physics next year. You scattering experiments. No, you're not doing it. Who's doing physics next year? No. Anyway, you're right. I can't really justify it from just this particular picture here, but his data justified that the center must be large, and by large I mean on the same scale as the alpha particle, not small like the electron. Yeah. Okay, so that's 3 marks only. Now the next part, which is for little babies, is A part 2. Describe the structure of the atom.
Describe.
Yeah. Include a diagram. Right, so, don't be stupid. What is in the center, the nucleus?
Neutron and proton.
Correct. Yeah, neutron and protons are in the center.
Outside.
And the outside is... Yeah. Here's an example. Here would be 2 electrons on the outside. So these are small negative.
Do you still have to write in words after drawing the diagram?
Yes, it says describe. And this is a large, and I'll put a little star here. There's a large compared to the electron, of course. Large and neutral neutron. And this here is large and positive proton. And my star is large compared to electron. Does anyone know how many times bigger roughly is the proton compared to the electron in terms of mass?
Like 4 times 10 to the power of 14?
No, not that much. It's about 1,000 times bigger. Not 10 to the 40s. Yeah.
We have 2 large and positive electron and neutron.
Yeah.
Why they didn't attract the electron to them? Like bring them.
This is actually something we have not done, which will be in your, if you do physics next year. And in fact, that's more of a chemistry question than a physics question.
Yeah.
And it's actually more of a quantum physics question than a physics we do. But it's not on this course why the electron is able to stay in this orbit. But it's the same.
It's like this. The proton is positive, the neutron is neutral. So it's kind of making the neutrons quite negative.
But the electron is small and the proton and neutron they are big and positive.
Yeah, that's what I'm saying. It's making the neutron a little bit quite
That's why they're
negative.
sticking together.
So
not
it's
being
repelling the proton, that's why there's a space between them.
In fact, look, I'll tell you something here now which will may shock you, but you've done, what are you doing in chemistry at the moment?
And equilibrium.
Yeah, so have you done orbitals?
Yes.
Yeah, what's the first orbital, the lowest one? The first, like if I have a hydrogen atom, which is just a proton, what's the absolute lowest first orbital? What's this electron configuration? 1s, and this is absolutely the lowest. And in physics we call that E1, the first energy level. Remember that?
Yeah.
And that's also called the ground state. Now, what is the path of this electron? What type of motion is it?
No, it keeps
Elliptical or circular? Yeah? Yeah? No. It's not this. In the... What's so funny? No. In the ground state, in, what do we call it? 1s. In this state, it's not moving in a circular orbit. I'm not joking. Its orbit is like this. It's vibrating in and out around the proton. It's not actually moving in a circle.
It's just stuck there. When it's active
and the reason it's too advanced for explain why it doesn't attach to the proton. Okay? But I'm saying, when you do this in chemistry and physics, we're looking at a very simplified picture. In fact, it's not traveling in a circular orbit here. I know Lorraine and I told you this because we're keeping it simple for IFY level physics, but in fact the electron orbit in 1s is not this. It's a kind of zigzag in-out pattern. There's no circular motion involved.
Kind of what?
A zigzag motion.
That's out of quiet.
Is it?
Yeah.
What does it mean?
Zigzag.
What's the next shell? What's the next one? What's the next one?
2s2 2p.
Yeah, so if I had the electron out here at E2, now it's traveling in a circle.
Because the electron before is repelling it or something?
No, don't try to understand it. You don't have enough physics yet to understand it. But I'm just saying the picture is much more complicated than how it's been presented so far. Now, the atom consists of a very small nucleus containing positively charged protons, and usually neutrons would have no charge. Electrons orbit the nucleus, they carry a negative charge, and the number of electrons is equal to the number of protons. Yeah, that's all fine. Alright, next question. Describe two properties of the strong nuclear force. State.
That's
Sorry.
A3.
A part 3.
State two properties of the
Now, I haven't actually said it in class, or if I have, you wouldn't have remembered anyways. I did actually say possibly that there are 4 forces in nature, 4 fundamental forces in nature. So, would you know any of the 4? What I mean? Gravitational force is 1.
Magnetic.
Yeah, we actually call it electromagnetic. Yeah, so we have magnetic, electromagnetic, and gravitational. They're 2.
We need some more.
Yeah. And the other 2 are strong nuclear and weak nuclear. So you know what gravitational does, we studied it, and you know what electromagnetic is, that's electric fields and magnetic fields. Strong nuclear force is what keeps the protons and the neutrons attached together. Because the neutron has no charge, correct? And the proton has a positive charge. So there's no reason for the neutron and the proton to stick together by an electromagnetic force. So there's actually another force which we don't study called the strong nuclear force, which keeps the center of the atom together. And 2 properties of it. First property is that it's strong. And the second property is, we say it has a short range. So this force only really works in the nucleus and doesn't extend out from the nucleus.
Even if you try to amplify it.
Yeah, it's a very short range force, not like gravity, okay? The sun is very far away, obviously. You can still feel the gravitational force from the sun. Okay, so gravitational can be a long range force. Do you understand? Yeah. What about electromagnetic? I think a magnetic force is pretty short, because if I have a magnet here, it would only really work for things which, you know, are close to it. It definitely wouldn't work like over by the window. Okay, so nuclear force is the shortest range. It only works within an atom. So the range here is on the scale of, you know, 10 to the minus 10 meters, and that's it. It doesn't work past this. Okay, the weak nuclear force Give me two properties of it.
Weak.
It's weak. Correct. Correct.
Long range?
And not that it's long. Well, it is that longer range. But well, I suppose yeah, it's longer range than the short. But another important thing about the weak nuclear force is that can I draw it here actually? You have your proton and you have your neutron. There's no charge attraction between them because one is positive and one is neutral. So what's keeping them stuck together is this strong nuclear force. However, there's actually another force which is pushing it apart. And this is called the weak nuclear force. Now, we have seen that before because remember we had our uranium-238 and it's decaying. What's coming off of it? The alpha particles and the beta particles and the gamma particles. But of course, if an alpha particle is fired out, there must have been some force that pushed it out. It didn't just come out by itself. And this is actually the weak nuclear force. Okay? So strong tries to keep it together. Weak tries to push it apart. In nuclear decay, which force is winning? Weak. But most of the time, which force is winning? The strong. This is why atoms don't collapse. Okay? Right, next now, B part 1. Super stupid easy. 22488 radium becomes something radon plus an alpha. Right, so let's complete it. What is the alpha? What do I write here? 4, 2, He, helium. Yeah. So then what number goes here? Correct. And what number goes here? 220. If you can do that, you have at least 3% of the exam. Okay? I mean, that question, that's easy. It's stupid, you know, like, I mean...
Yes, we have studied down.
What? Huh?
Yes, we have
Is it? I'll have to look at that. Right. The next one is convert the decay constant... Oh, what is the decay constant if they give you the half-life? So do you remember the formula for decay constant if they give you the half-life? Yeah, it's log 2 over the half-life. So what's the half-life here?
3.6
Yeah, so we'll keep it in days for the moment.
2.2 times 10 power minus.
Huh? 2.2? Oh, minus 6? No, you converted into seconds, did you? Hang on a sec. I put my calculator in some weird mode. Okay. Log 2 divided by 3.6. Taken, I'm going to keep it in days for the moment. 0.1925 and the unit?
Oh,
Half-life?
days.
Oh, sorry, decay constant. No.
No units. Days.
Per day.
Day.
It's almost there. Right. That was easy. Okay, continue that. So now the last part here, 3, part 1. You have n equals 1.85 times 10 to the 9 atoms. What's the activity? So what's the formula for activity?
A is equals to A0 minus lambda.
No exponential here. For this.
Lambda.
minus lambda.
Yeah.
Yeah.
What?
Should we change the second?
No, you don't have to. But the unit needs to be changed. So, well, hang on. No, I'm not using B quotes because I'm not using seconds. It's 356 mega atoms per day. That each day The rate is 356 mega atoms destroyed per day. The question doesn't specify what unit to use, so this is acceptable. What's the number 2? Determine the number of radium atoms remaining after 3 half-lives. Oh my goodness, so easy. How would you do this one? This is how many you have at the start. So what do you do next? Look, read the question and tell me. Read the question and tell me, and don't just shout your mouth off without thinking. What is it? Yes, good idea. Where is your paper actually? I printed these out for you. Where is yours? Oh, you have to put it down when you're carrying your shoes, isn't it?
Explain, sure.
No.
Half it 3 times.
Correct! Half it 3 times. So you half it once, half it again, and half it again. And this will be 231 mega atoms. No, it's how many you have, so it's just how many you have. Does that make sense? Like it's 3 half-lives, so you half it 3 times, Tekken. Does that make sense? Are you sure? Did you use exponential? Did you get the same answer?
Yeah.
Okay. Took longer though, didn't it? Yes. Right. Part 3. How long until you have this much? Okay, now we use this formula. What's the n? 3.65 times 10 to the 6. And the n0? 1.85 times 10 to the 9. And the lambda I had. What was the lambda I had?
Minus 0.01425.
1425. T.
What's T?
Time in days.
That's what we're finding.
That is what we are finding, KJ. Hey. Wait, hang on, is it... No, sorry, that's 10 to the 9. Where's your exam I gave you? I'm not... Oh, hang on just 1 second. What did you get, Tekken?
Roughly 50.
I got 43.7. Which...
What did you get?
What did you get to Tekken? 50 days? Did you give me...
43.7?
Dude, my constant is not 0.01425, whoever told me that. It's 0.1925.
You said 0.0125.
The heck is this thing here?
What? Looks like 0.
1925.
Yeah.
That's not even close to 0.01425. Let's do that again. Will you please get glasses, please? 0. No, 0. What's the lambda?
0.1925.
1925. I'm double checking. I don't trust anybody. I heard you the first time, Fahad. You don't need to prove it to me a second time. I promise. 1945. Was it? No, 1925. 32.4 days, yes.
Wow. That's very kind.
It is
32 points.
32.4.
Do we need to run down since that part is not so
Three significant figures. Right, have a look at these 6 now.
What's the mission of 6 or 4?
4.